Good afternoon, everyone. I hope you're having a good day so far. Today we're going to talk about beats, which is section 16.7 of this book. So, last week when we were talking about sound waves, we were assuming that they had the same frequency, the same amplitude, the same, they were basically identical in all fashions. Now we're going to wonder this week, what happens if they still have the same amplitude, but what if the frequency is a little bit different? So we have two waves here, and the green one we're going to say has frequency F1. And the black one we'll say has frequency F2. We don't know what those frequencies are, but we can tell because they have different wavelengths that they must correspondingly have different frequencies. So let's suppose you have, these are two sounds that are playing, and they're going to go, and we're out here somewhere, so I'll draw me over here in purple. And I'm listening to the sound waves. And so the question is, what will I hear over here? Well, since these two sound waves are both playing at the same time, they're going to interfere constructively and destructively in different places. And so our sound pattern is going to end up looking something like this. So you can see starting out, they're fairly close together, so they're additive. And we have some max constructive interference at the top, basically. So initially, we're going to have something that looks like this. It's going to look sinusoidal. And it's going to have an amplitude that's taller than either of the individual amplitudes. So it's all basically very close to twice the height of the individual ones. And then we can see that as we go on through time, they start getting a little bit different from each other. So we still have some pretty big constructive interference at our next time period. And then slowly our amplitude is going to change. And unfortunately, I didn't line this up very well, so these don't actually line up with the peaks. But so this is this peak, this is this trough, this is these peaks here. And what we're going to end up seeing when we get to, let's see, right here in the center, we can see so this peak and this trough, they're equal and opposite. They're basically going to completely cancel each other out. So for a stretch, we're going to have basically nothing happening. But then we're going to have some constructive interference again. And it's going to do something like this. And we get over here, we have max constructive interference. And then it's going to kind of drop off again. And we can see that this pattern, if we were to draw an envelope around it, so just kind of following the peaks and troughs we have, we could go like this. And then like this. We can basically fit our oscillations in between two sine waves. So this is kind of a pictorial representation of what's happening when we have two very close but slightly off frequencies. We're going to have places where the sound is going to sound really loud, about twice as loud as either of the individual sounds. And then it's going to get really quiet. And then it's going to get loud again. So are there any questions on sort of this conceptual introduction? All right, so let's talk about the mathematics. What happens mathematically? So we have these two waves, and they're interfering constructively and destructively, and they create this purple wave we have here. We want to know what is the frequency of this purple wave. Well, if these two waves are very close in frequency, then our new frequency is going to be approximately the mathematical average. And we call this our oscillatory frequency. line. So F sub OSC. So our purple lines here, their frequency is 1/2 of frequency 1 plus frequency 2. Now, what about this envelope here? What's going on with this? We also have what is called the beat frequency. Now, a beat is one soft, soft, or loud, soft, loud pattern. So going from, a node to another node, or from an antinode to an antinode, that's going to give you, that is going to correspond to the beat frequency. So the frequency is how many cycles you go through in a certain amount of time. So if we were to draw coordinate axes on here, so this would be time in seconds. And this would be, if it's sound waves, our amplitude is related to our pressure, so the change in pressure. And then, so if we give some time increments to this, so we'll say that this is 1, 2, 3, 4 seconds. So if you want to figure out what our beat frequency is from this graph, we're going to look and see, okay, this right here would be going from 2 seconds to 4 seconds. We complete one cycle in that time. So our beat frequency would be equal to 1 cycle per, we're going from 4 seconds to 2 seconds, so 4 seconds minus 2 seconds will give us 2 seconds, so 1 cycle in 2 seconds, or 0.50 hertz. So if we have a pictorial question like this, a graphical question, the way you find the beat frequency is you just figure out, find a cycle and figure out how much time it takes to complete that cycle. Now it's also the same thing as the difference between our two frequencies. So F beat is equal to, and we use the absolute value here because it doesn't matter which of our waves. So we had said that the green wave was F1 and the black wave was F2. We could have swapped it. We could have said the black wave was F1 and the green wave was F2. They're both equivalent, so it could equivalently be said, called F1 or F2 is just a label. So we take the absolute value sign, because if we were to get a negative sign out, it wouldn't have any physical meaning because it's arbitrary which one we call F1 and which one we call F2. So our beat frequency is just the absolute value of the difference between our two frequencies. So are there any questions on this so far? All right, so let's do an example. Let's suppose we have Cupcake and Joey again. So we have Cupcake over here and Joey over here. And they both meow simultaneously again. But this time, instead of meowing at the exact same frequency, their frequencies are slightly off. So, Cupcake's meow has frequency 350 hertz. And as you're listening to them meow, you can hear that the sound of their combined meows starts out really loud, becomes quiet, and then becomes loud again half a second later. So our time is half a second. And that loud, soft, loud pattern, that's one cycle. So it's 0.50 seconds for a cycle. Or for a beat. If Joey's meow is lower frequency than Cupcake's, what is the frequency of Joey's meow? So the first thing we have to do to figure this out is we need to determine our beat frequency. Now our beat frequency, we know that it takes 0.5 seconds for a cycle, so our beat frequency would just be one cycle per 0.50 seconds, which will give us 2 hertz. Now, to figure out what Joey's meow is, we're going to take into account the fact that his meow has a lower frequency than Cupcake's. So we would either add or subtract the beat frequency to Cupcake's meow to figure out Joey's. Since his is lower, that tells us to subtract. So we're going to have frequency of Joey's meow is equal to the frequency of Cupcake's minus our beat frequency. So this is equal to 350 hertz minus 2 hertz for 348 hertz. So just slightly lower. And even though we only have 2 sig figs here, we're going to keep the extra sig fig here just so the sounds look different. I'm not sure if the textbook does the same things, but I know some textbooks don't use the appropriate number of sig figs and still want the exact answer and not the rounded one. So if we were to round this, of course it would be 350, so they would be the same, but since there's a difference, we're just going to leave it as 348 hertz. So are there any questions on this one?
I just have a question.
Yep.
For the F beats, it's the absolute value.
Mm-hmm.
So if we have, I guess it doesn't matter, but if you were trying to figure out the frequency of the beats, if you had, can you give us an example where it would be a negative number?
It has to do with the arbitrariness of assigning beats. So if we say that F1 is 200 hertz and F2 is 190 hertz, if we wanted to find F2 minus F1, well, we'd have 190 minus 200, which would give us negative 10 hertz if we didn't take the absolute value sign. But since it's arbitrary, which one we call F1 and which one we call F2, because we could just as easily say that this one's F1 and this one's F2. That's why we kind of take the absolute value sign.
Okay, now I understand. Thank you.
No problem. Any other questions? All right, well, if there are no further questions, the beat frequency information was the last bit of stuff we needed to solve this week's homework. So that's all the material I have for you for today. If you do end up having any questions, you can always shoot me an email and I can respond to them that way. And have a great day.